Okay, here are now our new definitions. So we take a Ricci flow and we assume that it's defined on a time interval from 0 to capital T, where capital T is finite, and that's the singular time. So we don't have a type 1 assumption, but we do know that some curvature will have to blow up as we approach this capital T. And then we define the notion of type 1 singular points. If we have this kind of type 1 bounds, so we have that the supremum of Riemann is bounded from below by some little ci divided by the remaining time to the singularity, and bounded above by some capital Ci divided by this. And that happens on a neighborhood of the point Pt. So what this neighborhood is explained below. We will go into that in a second. So if we don't have such an upper bound, if we instead have that this lim sup is equal to infinity, then we call the point a type 2 singular point. Okay, now let's look at what this neighborhood is. So this is a parabolic cylinder, and it's important, so this is new, we use a forwards and backwards parabolic cylinder. Okay, so the picture is this. So we have this point here, which is P at time t, and then we look at a geodesic ball in the metric at this time, and we cross it forwards and backwards with this time interval, which goes from t minus r squared to t plus r squared. Okay, so that's a parabolic cylinder. It's important that we use a square for the time and no square in the linear in the space direction. I wanted to say a linear factor. Okay, so that means if we want to write this out here, so this is the parabolic cylinder. It's a ball of radius Ri times the root of the remaining time to the singularity, cross the interval from t minus Ri square t minus t and t plus Ri square capital T minus t. So this in particular shows that this makes only sense if this Ri is less than 1. Okay, and again, so if we locally have these bounds both below and above of Riemann times the remaining time to the singularity, then we call this a type 1 singular point, and if we don't have an upper bound, we call it a type 2 singular point. Okay, our first theorem then, which in a certain sense generalizes the theorem C from before, is the following. I call it theorem C dash because it's sort of a generalization or localization of this theorem C of Enders, Topping, and myself that we have seen before. So here we have a Ricci flow, and it's important we do not have any global type 1 assumption. And then we have that the singular points are exactly the type 1 and the type 2 singular points. So it's clear that this is a disjoint union, and it's clear that if we are in one of these conditions, then we must have a singular point. But the difficult part is really to show that there are no other singular points. In particular, this shows again that the Riemann tensor blows up at least at this type 1 rate. So it always satisfies this lower bound for how the curvature blows up. Where previously we needed an upper type 1 bound to get the lower bound. And here we can show that whenever the point is singular, so meaning that whenever in some neighborhood Riemann blows up, then it always blows up at least at that rate. And then we have a similar result for the Ricci singular set. So the Ricci singular set is defined exactly the same way as the Riemann singular set, but replacing the Riemann tensor with the Ricci tensor. Okay, so also the Ricci curvature, if it blows up, then it blows up at least at this type 1 rate. Okay, it cannot blow up without this lower type 1 bound. That's the first result. And then the second result is, in a certain sense, a generalization of Sessum's result. That's why I call it theorem A dash. That says if you have a Ricci flow, complete bounded curvature time slices, then the singular set is equal to the Ricci singular set. Meaning, if there are points where the Riemann tensor blows up in a neighborhood of the point, then also the Ricci tensor must blow up in a neighborhood of that point. Okay. In particular, we cannot have, so Sessum basically just tells us if we approach a singular time, then Ricci blows up somewhere. But we don't know how fast it blows up somewhere, and we don't know whether it blows up at all the singular points. Now, this theorem says, unless Ricci blows up, we can't have a singular point. Okay. So let's look a little bit at how one proves these theorems. Okay, so what is the idea of the proofs of the first theorem? So of the fact that the singular set is equal to the union of type 1 and type 2 singular points. Okay, so we first of all introduce this regularity scale. So this regularity scale says the following. So we say that the Riemann scale or regularity scale is at least R if we have a bound on the Riemann tensor by R to the minus 2 on a parabolic forwards and backwards cylinder of size R. So that means if we want to have Riemann very low, very small, so then we have an R which becomes larger. So meaning if the scale becomes larger, then we have lower curvature. And we do not just have this at the point, but we have this on a bigger ball also. Okay? If this scale becomes small, then we have a worse bound, and we also have it on a smaller region. Okay? So this is a way of at the same time measuring how large Riemann becomes, but also measuring sort of a size of where this happens. Okay? And that's this regularity scale. Let me maybe say that regularity scales that are similar to this one have been used before. So based on balls here at the fixed time, or also on backwards cylinders. But we study this on forwards and backwards cylinder. And the fact that we do this on cylinders that also go forwards in time is actually very essential for us. And we cannot prove our results unless we use this definition. Okay, so let me say a little bit more about what we know about this regularity scale. So we can show that it is Lipschitz continuous in space. So how do we prove that? So assume that we have this point PT, and we have the blue cylinder is the forwards-backwards cylinder of size being exactly this Riemann scale. So then we have on the blue region, we have these Riemann bounds, okay? And then in order to show that this is Lipschitz continuous, we just show that if we move the point at the same time, so in this time slice, we move to a point QT, then this smaller red parabolic cylinder is still contained in the bigger one if we define R to be the radius of the blue one minus the distance between P and Q. And basically this follows trivially from a triangle inequality in space, and in time it's even easier. Okay. Now we also prove that this is Hölder continuous in time, and that's a little bit more difficult. So one might think that the idea is the same. So now we say we fix a point P, but we move, for example, forwards in time to a time S. So now we want to put a smaller green parabolic cylinder around this point PS. Okay, and we want to again show that this smaller one is contained in the blue larger one. Okay, but this time it's very tricky how we define the size, and the reason for that is that here the radius is taken with the metric at time g, but here the radius in space, or the distance in space, is taken with the metric at time s. And this metric changes, so measuring here the same size doesn't mean we go out up to the blue region again. It means we go out now with a new metric, and we might go out much further or much less, depending on how the metric evolved and whether it was shrinking or expanding. So we need to be very careful, and we can show that this is still true if we define the radius at this point as the radius that we used for the blue one minus a constant times square root t minus s. So because of the square root we get the Hölder continuity, so it's a 1/2 Hölder estimate. And this constant we can actually write down explicitly. It's 2 times the 4th root of 2/3 times root of n minus 1. And the reason why this works is because we have control of Riemann on the whole blue cylinder. So in particular, we know how the metric evolves inside this blue cylinder. So as long as we don't go out of the blue cylinder, we actually know that the metric here at time s is still somehow related to the metric that we had here at time t. And so the main ingredient are these distance distortion estimates that we can do in this blue region. Okay, so that's the first part, introducing this regularity scale. Then the next step is that we can now give an alternative characterization of the singular set. So we have defined the singular set by saying that on some parabolic cylinder we have some upper and lower bounds in the type 1 case. So now this translates actually to upper and lower bounds for possibly different constants, ci tilde and capital Ci tilde, or C1, so it's a kind of type 1 bound for this regularity scale with exponent -2. So remember that the regularity scale with exponent -2 is basically bounding Riemann. So this sort of still says that Riemann is bounded above and below in a way similar to before. And then we say we have a type 2 point if instead this quantity goes to infinity. And in general, we have a singular point if and only if this Riemann scale to the -2 goes to infinity. Or in other words, if the original Riemann scale goes to 0. And while it's actually relatively easy to go from the definition that we have seen to point 2 and point 3 here, to these alternative characterizations, because we already defined type 1 and type 2 points using these parabolic cylinders. We haven't defined singular points using parabolic cylinders or using some regularity scale. We just said a point is singular if there is a region or it's regular if there's a region on which Riemann stays bounded, or a neighborhood of P on which Riemann stays bounded. It's singular if for every neighborhood of the point instead Riemann blows up. But we don't know how large this neighborhood is, and we don't know at what scale Riemann blows up. So the first part, therefore, is the most difficult to show. And one direction is still relatively easy. Now I'm showing only the other direction. So I assume that we do not have this property. So I assume that we don't have that the lim sup of the regularity scale to the -2 is infinity. Or in other words, we don't have lim inf of the regularity scale with exponent 1 going to 0. Okay? So if we don't have that, that means at least for very late times, we have some lower bound. So we have a definite size at a very late time, almost a singular time, where we have this cylinder, the blue one, which is the regularity scale cylinder at this late time. Then again, we can go to this earlier time and see that at this early time, because we have control of Riemann in the whole blue region, we know that here we can put a ball of a definite size that we can actually estimate precisely inside this, say, first time slice of the blue cylinder. And then we look at this parabolic cylinder that corresponds to that size. And then we iterate and we go further and further back. And while each time we might have to make these cylinders a bit smaller, we can actually control how much smaller we have to make them. And we can go back all the way to our original metric with this. And then we find this, this black region, which always lies inside these cylinders and on which we have curvature bounds. So now we have curvature bounds, and they extend all the way to the singular time. So let's assume the top line here is exactly our singular time. And that means that the point cannot have been a singular point. So we have shown if it was a singular point, then we must have lim sup equal to infinity. And then, as I said, the other direction is relatively easy. Okay, and then a third step and last step is that we now have this alternative characterization, and we still need to show that whenever we have a singular point, then it's either in type 1 or in type 2. So it's clear that if we are in the type 1 set or in the type 2 set, then necessarily this quantity needs to blow up. So necessarily we have a singular point. What we want to show is the other direction. Okay? And the other direction, we can actually show that if we have a singular point, then this regularity scale must actually blow up at least at this rate 1 over the remaining time to the singularity. Okay? And the reason for this is actually quite simple. So if we have this point PT, if we would have a if we don't have this bound, so if Riemann to the -2 is smaller than 1, that means that the original Riemann scale is strictly bigger than the time it takes to the singular time. So R square would be strictly bigger than capital T minus little t, and that would mean that the cylinder would actually go beyond the singular time. So in particular, we can go all the way to the singular time and have still curvature bounds. But that's of course a contradiction to the fact that P is a singular point, because that means we can't have a neighborhood in which we have curvature bounds all the way up to the singular time. Okay, and that proves that last step. So basically the type 1 blow up in our case is already built into the definition in a certain sense. Let's have a look at the idea of the proof of the second theorem. So the second theorem is a bit more complicated. This is the generalization of Sessum's result. So how do we do this? Okay, so we assume that we have a point which is singular but is not Ricci singular, meaning we know that the Riemann curvature blows up on every neighborhood, but the Ricci curvature does not necessarily blow up. So we can find some neighborhood of P on which Ricci remains bounded. Okay, then we translate again to our regularity scales that we have used before. Okay, and we can, in the same way that we have defined the Riemann regularity scale, we can also define a Ricci regularity scale. Okay, now we do have, if the point is not a Ricci singular point, then its Ricci regularity scale does not go to 0, meaning it's bounded below by some delta. Okay, and this of course uses again the continuity property. While the Riemann scale does go to 0, or at least along a sequence it goes to 0, so we can find the sequence of times for which Riemann is bounded by, say, 1 over I, and that obviously goes to 0 as I goes to infinity. Okay? Then what we would want to do is we would want to take some blow-up limit. But the problem is that at this point P, we actually don't have very good information. So what we do instead, and that's a very nice idea that we have found in a paper of Hein and Neighbor, we go to a point Qi, which is the minimizer of this quantity. So it's the minimizer of the quantity regularity scale at Q divided by the distance to the boundary of the fixed size delta ball. Okay? So in particular, once we have found a point where this is minimal, we know that Ri, which is the value of the regularity scale at this point, Qi, must be less than the regularity scale at the point P. Because obviously, if we move away from P, then we have decreased this distance to the boundary. So if the distance to the boundary is smaller, and nevertheless we're getting a smaller value than we had at P, that means that also the denominator would have to be smaller. Okay? So this means we have found a point, Qi, where we still have that the regularity scale goes to 0. Okay? That is the first property. And then we look at these rescaled flows. The rescaled flows are just we rescale with this regularity scale to the -2. So that means the regularity scale becomes very small. So Ri to the -2 again becomes very large. So we're blowing up. This is a large constant, and here we divide by something large. And then we obtain these rescaled flows, and they exist on this time interval. And now this is this formula here is just from the parabolic rescaling. And then from what we have done in the previous theorem, we know that the regularity scale always blows up at least at a certain rate. So that the regularity scale to the -2 times t minus ti is always at least 1. Okay, that was the last point on the previous slide. Okay, now we have looked at these rescaled flows. So we introduce this quantity di, that's a half the distance of Qi to the boundary of the ball, and that's the original delta ball, but now rescaled. So we're working in this rescaled metric. And we want to see this distance from qi to the boundary, how that behaves. Okay, so just by the original formula here, this is gonna give us something like the new regularity scale at the point qi, but we have rescaled in such a way that the regularity scale has become 1, so that's 1, divided by the function w at the point qi, and then we also have the factor 1/2 here. Okay, but we do know that this value, because again we're using a minimizer, the value of wi at q, or at qi, is less than the value at the point p, and at the point p the value we get is 1/i and then divided by delta, so 1/i delta, and if we take 1 this we get I delta, and then the factor 1/2 just remains. Okay, good. So now of course we have I going to infinity, so this distance di goes to infinity. So what does this mean? This means that after rescaling, the point qi lies further and further from this rescaled ball. Okay, or from this boundary of this rescaled ball, I wanted to say. So while here we only know that the minimizer clearly lies in the interior, because if the distance goes to 0, then this denominator is going to 0, and the whole thing blows up, becomes large. So the minimizer is certainly not at the boundary, but it might possibly be closer and closer to the boundary. Now this argument shows that this actually can't happen, in particular after rescaling with these larger and larger numbers, the distance to the boundary actually goes to infinity. Okay, now we have defined this as 1/2 times the distance to the boundary. So this means every point inside the ball of a radius di has still another 1/2 distance to the boundary left, so it's still at least distance di from the boundary. Which means that for each point q, we can actually look at the radius di ball around q if we want to. Okay. Now what we do is we look at these points q, they're lying in this ball, and what we do is we look at 1/2 times di, so by the formula that we have just shown above, this is the same as this w functional at qi, and now qi is the minimizer, so this is less than the w functional at the point q, and by definition, what is the w functional at the point q? It's the same as the Riemann scale divided by the distance, and the distance is at least di, so it's definitely bounded by this number. Okay, so what does that mean? If I multiply by di on both sides, I get that the Riemann scale, so this is all for the rescaled flows, at q is bounded below by 1/2. Okay, so that looks like a very good property, because we have seen that Riemann scale being bounded below means we have actual Riemann bounds, so Riemann actually bounded above on a ball of a fixed size. Okay, and because we have these bounds in this entire ball of radius di, where di becomes larger and larger, we actually have Riemann bounds on larger and larger balls. So this is an optimal property. Let's write this up. So we have Riemann bounds, and these Riemann bounds are actually 4, because if the Riemann scale is bounded by 1/2, Riemann is bounded by Riemann scale to the -2, so that gives us a 4. So Riemann is bounded above and below, or in norm is bounded above by 4. And that happens on a larger and larger region. Okay, and that allows us to extract now a pointed smooth Cheeger-Gromov limit for our rescaled flows. And this limit is a complete manifold, and it's at least defined for times between -1/4 and 1/4. And for the Ricci flow experts among you, so the precise result we use for this is Topping's compactness result, which is a generalization of Hamilton's compactness theorem for Ricci flows. Okay, now let's see what are the properties that the limit flow inherits. So firstly, we do have that the Riemann scale at the points qi, 0 was always 1, and that passes to the limit. So in particular, the Riemann scale of the limit object at the limit point is still equal to 1. And then the Riemann bounds, they also pass to the limit. So in particular, the limit object has Riemann bounded by 4 everywhere. Okay. Secondly, we deduce from this inclusion that the d eyeball in this rescaled metric is contained in the delta ball of the original metric. We know that we have on this delta ball we had the Ricci bounds, and that translates into Ricci bounds for the rescaled metrics. So the rescaled metrics, while the original ones had Ricci bounded by delta to the -2, the rescaled ones have Ricci bounded by Ri square delta to the -2. So forget about this factor A0. So this is the factor that we plug into the definition of Ricci scale, and that's just an explicit constant. Okay, so remember that this Ri was going to 0. In particular, our Ricci bounds become smaller and smaller, and in the limit actually we have that the limit object must be Ricci flat, must have vanishing Ricci curvature. But if we have vanishing Ricci curvature, that means that we're not even evolving on the Ricci flow, we just get a static Ricci flat metric where nothing happens. Okay? And this is essentially the same situation as Natasha's sum obtained, just in her proof it was much more direct because it all worked on a global scale instead of a local one. And then by a method which is similar to the one of Natasha's sum, and what she actually uses is a volume comparison argument, which we can basically copy almost verbatim. We obtain that the limit must be a flat plane. And the reason for that is that one can show that one is in the equality case of the Bishop-Gromov inequality, and the equality case only happens on the plane. But if the limit is a plane, that of course contradicts the fact that the Riemann scale at one point was 1, because the Riemann scale otherwise on a plane would be much larger than 1, but it is actually 1. Okay, and that's a desired contradiction, so that means we can never be in the situation where Riemann blows up, but Ricci stays bounded at a singular point. Okay, so as I said before, there's this open conjecture which says that it's unclear whether a bound on scalar curvature should be sufficient to give extension theorem for the Ricci flow. And it might be true in low dimensions, it's definitely true in dimension 2 and 3, but in arbitrary dimension 1 expects counterexamples. But we can prove the following. So we can prove the result which says if you have a Ricci flow, assume that it's closed and has dimension less than 8 and a uniform bound on scalar curvature. So for all times up to the singular time or up to the time capital T, we will see in a second that it's actually not a singular time, but a priori it might be. So for all times up to capital T, we have scalar curvature, uniformly bounded. And then what we also need is this technical assumption on an injectivity radius bound. So while we do allow the injectivity radius to collapse, so we have here the maximum of Ricci, but Ricci might blow up, so this might become a very large number, and then to the exponent minus 1/2 might become very small or might go to 0. So we do allow the injectivity radius to collapse, but only at a controlled speed. And in a certain sense, this corresponds to a Ricci scale non-collapsing of the flow. Then we can always extend the flow smoothly past time capital T. And then we have another result where we don't need this injectivity radius bound, but instead we assume that the points are in a certain sense well behaved. What does that mean? So we assume that at least if the Ricci curvature is sufficiently large, or if Ricci scale to the -2 is sufficiently large, then the Ricci curvature is actually also at least of a definite size, which compares to its Ricci scale. So what does that mean is we can't have points where Ricci is basically 0 or close to 0, but in a neighborhood of the point it's very large. So it also, in other words, means that Ricci can't decay extremely fast from its maximum. If we have this technical condition, then we can show that the singular set is empty in dimension n less than 8. So again, we can extend the flow smoothly past time capital T. And in dimensions higher than 8, we have a codimension 8 result in a suitable sense. Okay. Let me also say a few words about how these results are proven. So for these well-behaved points or under the injectivity radius bound, we can actually show that the Ricci scale is bounded from below by a constant times the Riemann scale. And the important thing is this is the Ricci scale squared is bounded below by the Riemann scale without a square. Okay? So let me say 2 words about this. So this, we can always prove that Ricci and Riemann themselves have a relation of this type when we have bounded scalar curvature on a region of size of the Riemann scale. Okay? But the Ricci scale might be much larger. So to have a comparison of the actual scales, we don't just need to have this comparison on the parabolic cylinder of size Riemann scale, but we need to have it on the size of Ricci scale. And that is the hard bit, and that is the bit where these assumptions come in. Okay? To extend the inequality that we have between Ricci and Riemann, the tensors themselves, not the scales, that we have on the small scale, to extend them to the larger scale, which is the Ricci scale. Okay? And as I said, there's various ways of doing that under some extra assumptions so far. So we expect that something like this should hopefully be true without these extra assumptions of injectivity, radius bound, or well-behaved points, but currently we can't prove this yet. So if we have this inequality, then what we can do is we can look at the integrability results proved by Baumler for the Riemann scale. So he uses a slightly different Riemann scale than the one we use, but we can actually adapt this to our Riemann scale. So we get basically his results, which say that some integral of the Riemann scale, we can use that one, is definitely bounded. Okay, and what we actually need, so he uses Riemann, so we need Riemann scale to the -2. So we integrate Riemann scale to the -2, and that is bounded by a fixed number, or actually if we, depending on what size we work, this integral will go to 0. Then we use our theorem A', which says every Riemann singular point is also a Ricci singular point. We use this comparison, and we use the fact that a Ricci singular point must have some integral Ricci curvature concentration, so that the corresponding Ricci integral, but this now has a different exponent. So if we use Riemann to the -2, then we get Ricci to the exponent -4 in the comparison, and that actually cannot go to 0. Okay, and that's our Ricci concentration result, and that will give a contradiction. So we use this estimate and Baumler's integrability, and also a new integrability or new concentration result for the curvature at singular points. Okay, good, and that proves these theorems. Let me just say a quick remark about this property. So if one can show that this always holds, then what one can do is one can prove the previous theorems without any extra assumptions at all. So we can prove that the Ricci flow does not develop singularities with bounded scalar curvature up to dimension 7, and from dimension n larger or equal to 8 onwards, we have always codimension 8 singular set. Another thing one can prove, if this always holds, is that the flow cannot develop any type 1 singular point. So every singular point is necessarily a type 2 singular point. And what we're currently doing is we try to use something similar to the theorem B, which uses a blow-up result to show that the scalar curvature must blow up under a global type 1 assumption. We try to do this under a local type 1 assumption. So at a type 1 singular point, try to take a blow-up and show that then at this type 1 point, the scalar curvature also has to blow up. So we try to find a way to prove directly that a bounded scalar curvature flow cannot have type 1 singular points without using this inequality. And that would be a very easy consequence of this inequality if that would always be true. Okay. And that was my talk. So thank you for your attention, and see you.